So I would like to share a project that I'm currently working on. Its name is I call it logic code. So basically what it does, it allows you to simulate logic circuits and something similar to Verilog, but it's very small and simple, like anyone could understand that. Even you can't consider it as a programming language. Okay, so I'll say how it happens. So the main strategy or how it works is we write something called a logic code. Okay, for example, here we are going to create a flip-flop. Okay, so we will define flip-flop.lc. okay, so once we have written some script, I will show you how it's written, the formats and all. So after you have written that, it will be converted to a C file, okay, and also it will generate a make file for that, so you can simply build that. Once you have completed building that, you can just run it. Okay, that's the main strategy here. So we also have some standard libraries here. So it has some of the standard like NAND or NAND. Since you can't like go deeper levels, like if you want to define we can't define transistors and all. Like if you define those things, like it will become some more sort of a electrical, and I believe that will slow down everything, and it makes more complex and all. You just want to mess around with this logic system. Okay, you just want to know like, and you don't want to know what happening behind. Just if you give out to output, you want the and out of these two. So similar like that, you have NAND and all here. So here we are going to define a flip-flop. Okay, so this is the basic diagram we are of a flip-flop. Okay, we will see how we are defining that in logic code. So just go here. Okay. So first of all, you have to define this module or something similar to class, and I believe there is also module in Verilog and all. Okay, so it's something similar. You have to define module. So what module does it? It creates a definition or a blueprint for your module or component. Okay, so we are having the flip-flop. So we will define flip-flop. Then what you need is module. Okay, then you need to define the input and output. Okay, that's like you have to put a normal bracket, and you need two square brackets, like, and in between you should have this arrow. Okay, so what it does is, the first one is like the input. This is input, and these are the output. Okay, so in this case we want R and S here, and outputs are Q and NQ. So here we will define R comma S, and here it is Q comma NQ. Now you need to open, you are going to define what all are things inside. But before that, like we have said, we need this NAND and all, so we will input or include this standard library here. Okay, I just call it standard. Okay, so to do that, like we can include a standard library like C file here, or else you can define the logic code itself using other command called copy. But here we are only using the basic gates, like the ones like NAND and all, so we just need include. So include, then bracket, then the string. So it's like the directory is like stdlib libs. Okay, then we have the standard gates. You don't need to provide this this extension here, because it reads this JSON for some of the information regarding these gates, and it does all automatically other than, okay. So you need to define only stdlib/standard gates. Okay, once you have defined this here, you can use it here. But here we have something called contain. Okay, contains. Okay, contains. Here we define what all the modules or components we need in this module. Like even if you have if you're defining something like a latch or something, you can actually use flip-flop inside here. But you so in this case we are using NAND. Okay, so NAND 2. Why this 2 comes? It defines like 2 input NAND gate. Okay, or if you want need 3 input, just give. These are all defined here. You can see NAND 2 gate and all. Okay, and you have to give the name. Like here we will define NAND A, comma NAND B. Okay, that's all. So you have defined there are 2 gates. Then we need something called wire. Wire is something unlike the Verilog and all. Wire is not a component in our case, because you just in this wire module you just have to say what to connect, and there are some of the restrictions or rules you have to follow while connecting the wires. Some basic system is like you have to connect, if you are having this as what input to a module to the input of a, okay, this R should, from R you should connect to A, not A to R. Okay, and I believe that we will define in another video, or we will mention more information about that in another video. Okay, so we will define this R connects to this NAND A dot A, and S connects to NAND B dot B. Okay, now we have connected these 2 connections. Next we will connect these 2 connections. Okay, for that also there are some restrictions, but we are now, I'm not going to mention it right now. Okay, NAND B dot O. Okay, so O will connect to NAND A dot B. Okay, that is B dot O will connect to A dot B, and next is NAND A dot O will connect to NAND B dot A. That is this connection. A dot O will connect to NAND B dot A. Okay, now we need the next connection, that is this output connection. Okay, so NAND A dot O will also connect to Q. We have defined this Q here, no need to define other than that. Which is NAND B will dot O will connect to NQ. That also we have defined here. Now we have completed the wire and all. Now next we need something called init. Okay, init is some that defines the initial states. Like in real life this automatically happens, or like this Q and NQ, or there will be some errors, like you can't have this Q and NQ to be same, like that sort of error. So in that case you can define what is the Q and NQ initially, so that it will avoid some of the errors. And there is, so okay, that's how. So while defining init you have to mention it in square brackets. So NAND A dot O will be, just put equal, then square brackets 0. That means, and also NAND B dot O will be B will be 1. Okay, so we have said this will be 0 initially and this will be 1 initially. Okay, next component. Okay, you may say like you can just do it in one line in Verilog, and we are writing so long. Yeah, I know that, but these are like, this makes sense, right? I believe so. If you're not a fan of this, okay, no problem, you can just continue with Verilog. And I believe that it's like for small noob guys. Okay, so we are here in process. What process does is like it says the order in which the components have to be processed. Why we need that is because in real life these are like asynchronous or does in parallel, or there is whenever you put an output, whenever you put an input to the system, it will give output, and at the same time you can give this to the other gates, and both of them will give output. But our system or our computer or any other, not any other, but basically our computer systems are designed for this serial. It can do only one instruction at a time in deeper levels. Okay, you can there are some parallel or threading and all, but we don't want to, at present don't want to go that deep. So we have to define the order. So if we automatically generate, there is an issue like if you consider having another component here in before this gate. Okay, the problem is like if you process this one, the NAND A first, before processing the gate before that, it could cause an error. So to avoid that, we will define the order like it should be processed before that, and manually doing, I believe that's the best method to do. So we can do this is also an alternate thing we have introduced in this language. Okay, so NAND B semicolon, that's all. Okay, yeah, the alternate method is like there will be multiple updates at a point. That's called UPP, or updates per point. You can define 1 or 2 or n times updates. You can ask it to do this 5 times 3 times update before giving the output. So that will be a correct, even if you if you are in the wrong order also, that will help you get a correct answer. So this is our module. Okay, we have defined that there are 2 gates. We have to connect this and this, and initial values of Q and NQ will be this, and while you are calculating the output, just do it in this order. Okay, that's what we have defined in flip-flop. Like I said, this only acts as something like a reference. If you want to do, or if you want, like in case of real life, you have a chip. If you want to run that, you need let's consider you need a breadboard, power source, everything like that. So for this breadboard kind of idea, or if you want to use this, you have introduced something called workspace. Okay, workspace, we will define something similar to this module, but it doesn't have any name. Okay, just workspace semicolon here, and here also you have to define this inputs and outputs. If you don't have any input, you can just put like this. Okay, it is necessary you have to put the square bracket. If you don't have anything, just put empty square brackets. Okay, then we will have A comma B here, 2 inputs A and B, and output maybe like C and D. Okay, C comma D. Now we have defined, I have not drawn it here. Yeah, here we will define that. Okay, just a small picture. Okay, I have not drawn this here, but you can consider like there is an input A and there is an output input B, and you have to connect this A to R and B to S, then Q to C and NQ to D. Okay, that's what here doing here. Not only you can do this here, you can actually define multiple like NAND or and just combine all these modules as you like. Okay, so here also we have this first container. Okay, here we only have this flip-flop, like flip-flop, then FF. Now we have got the flip-flop. Next what we need is the wires. Okay, we will define the wire, then just imagine we have to connect this A to R, so we will define connect A arrows to FF dot R, and where this and come from is here. We have defined this here. Okay, that's the R. If you have defined any other variable, you have to define the same here. Then B will connect to FF dot S. Then you need to connect Q will connect to our C, and NQ these all are here. Okay, NQ will connect to D, and here is a problem, that is how to define FF dot. Okay, FF is the flip-flop we have defined here. If you want, you can define FF1, FF2, or n times you can define here, but here we have already defined once. Okay, so we have connected the connections. Next, here we can define init. Since we have initialized here, it is not necessary to define init here, but I will show you some other thing called, as I have mentioned, you can define the UPP or updates per point. You can just define here UPP. There are multiple ways to set the UPP. One method is here, you can define UPP here, just UPP equal to your value. Okay, that's all. And but I believe I will show you another method, so we'll just remove that here. So it's not necessary. If you don't want init, just remove that. Okay, so process however is necessary here, because here also, even though we have only one element, we have to process that. Okay, you have to mention in process. Okay, so we have just defined the process, and I believe that's all you have to do. We have connected the circuit, then we have defined we need a flip-flop, and flip-flop we have defined above. Then we need to do the connections like this, then process FF. Process is like something what you call every loop. Okay, and that's all, we have done everything. And now, as I have said, we have to make it a C file, and if you need, like, you can do it an intermediate state. I will show you how does it. Okay, this project actually runs using this Mojis and nearly. Okay, so if you want, you can do this node. Okay, you can just see, I will show you how the JSON will look like. Okay, dlab pass. Okay, there's an issue that we have to be working directly, because this is our currently running project and it uses these scripts here, so you have to go to that folder. Okay, cd dlab, right? Okay, believe that's okay. So no, sorry, okay, we are correct directory. Okay, we have 10 digital labs and we are here. These are the scripts that require. Okay, so we are in the correct directory. Sorry. Okay, so we will clear that. And now dlab, then before that we need node. Okay, node dlab, then pass, then the file name, which that is flipflop.lc. Before that we have, it is in working directory, so we'll define working directory, then flipflop.lc. Now this is the front directory. We will read from this directory and generate the file. Since this going to generate a JSON file, not a C file, I just want to show you the JSON format. So we'll define the same file, then ffjs and .json. Okay, and just send. We can see it has generated. Okay, the JSON file. This is the intermediate JSON file that it's gonna generate, and okay, it's too long. If you want, you can do that, or else just directly convert it into C file. For that, the command is same. Here you have to just define. The another issue here is like the same. You have to be define the same name here now. Okay, that's a current issue with the. I will show you what it does. Okay, just have to flipflop dot cpp. Okay, and here instead of us we need gen. Okay, it's generate. Okay, just so we will read this and generate a cpp file. And okay, why? Okay, it has generated. Why this ff you need the same name right now? Okay, I will fix that in the next update or something. This is actually a prototype. It's not even published or even in I have not committed to GitHub and all. So why? It's because it automatically generates a make file for you, so you don't have to mess around with if you are using the default configurations and all. So here we have this flip-flop. So if you change it to any other name, that also affects here. So you have to change or modify some of the contents here in order to make run the make properly. That's why I said you have to give this name properly. Okay, so it automatically generated the make file. Also, if you want, you can here is the JSON. Okay, it's okay, this is some of the config that it generated. You can change anything here and run the region. I feel like it make more sense to run. Okay, if you change anything and type a remake, that will just generate the make file for that config. Okay, that's not necessary. Okay, so once we have that, we will run the make here, but make is inside the working directory. So working directory, then make, then our file name, that is flip-flop. Okay, now we will run that. There is some issue. Okay, what happened? Okay, we'll check that. Okay, and flip-flop here also, and cpp. Where is the flip-flop dot? Okay, there is an issue. Like, okay, this is the what I have. We have flip. Okay, instead you have to. That's the issue that I have mentioned. Okay, so you have to change this one. It's saying like flip-flop. There is no. So if you are good at this thing, you can do that, or else simply okay, generated a flip-flop. Just go to flip-flop. Okay. In this case it work. Okay, you have to understand the make file before working with this. Okay, I believe that's gonna fix that issue. Yeah, okay, it has generated the object files here, and then it has also generated the executable or binary file here, so you can run this to get your output. Okay, so I will move to this build file. Okay, build file, and you can see, if you type flip-flop, you will see there are mode not provided. That's because there are different modes you can run this. Okay, so like you can give direct mode, direct mode does is like you have providing the inputs directly, like input, that's why we will give first of all A and B, A to be 1 and B to be 0. And how I said it's A and it's B, it's because it follows this current order, the order in which you have defined the inputs here. Okay, that's the way you have to give, and if you give enter, it will process and give the its state like C and D. That's here we have defined the initial states here. Okay, that's why it shows here the initial states C and D, C0 and D1, and when applying this 1 and 0, it give you, it's the condition for the reset itself, so it again show this thing. So if you want, you can change this to 1 and 0. Now it's a set condition, you can see it was set. Okay, it is now Q is 1. Okay, that's one mode. Another mode is like you can give interactive mode. Interactive, and what it does is it will give you a shell. Oh, I don't want to say shell, it's like a program you can directly give the input and see the output, and it's like it's doesn't change. 0 1 it gives you the output, 0 0 it will give you the error output, then 1 1 it will like that's what. Okay, it's an interactive mode. And the final mode is the file mode. Okay, if you go here, you can see there is an input or inp.csv. it's a file that defines like these are the inputs A and B. You can do it in any manner. Okay, and this person doesn't have any function right now, but I believe I'm trying to do it in like generating the wave and all for this GTK wave and all, and I'm messing with this LTX format and all. I don't know like when it will be ready, or and I don't know even if it's gonna work, because it seems very hard to find the format and also for this LTX file. And so if anyone is having a resource or something related on the structure or how to write this or generate LTX or any other format that GTK Wave and all uses, try sharing. Okay, so that's what these are. It's the UPP, that's one you have defined here. Instead you can also define here also in the input file. Okay, like here we have 5. If you want 7, you just say 7 and run that. And so what it does is like it reads the output file and outputs that. Okay, so and generates the output here. So you have to define the file name. Okay, that's okay, just give that, and it's processed at 7. Okay, 7. So you have this, that's the output you get. This is the same order that's here what you have defined here. Okay, A B C D, this is not here, A B C D. Okay, that's what the file mode is. Okay, right now this is the state my project is. I believe that it would be beneficial for some of the guys. I don't say it's gonna like very much big or powerful as Verilog or any other hardware description language. I believe these are gonna help these noobs and all those who are starting with trying to simulate this logic circuits and all. So like writing makes like you can understand what it defines, right? Simply defining this you can't understand. So I believe that's gonna help someone. That's why I'm doing this project. Also, someday I don't think that soon, but someday we'll be able to do the FPGA programming, I guess. Some guys gonna comment like you can do the Verilog just flip-flop in just one line, you don't need these many lines and all. Yeah, I know that. Okay, but yeah, it's not going to show you what it is. Okay, it physically is. You are just defining the formulation and all. I know there are different levels you can do in Verilog and all, but I feel this more comfortable for me, not for everyone. Okay, it depends, I know. Okay, that's my project. Thank you.